Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the failure analysis of the weld joints. In this particular presentation, we will be talking about the failure analysis related with the austenitic stainless steel weld joints. So, austenitic stainless steel is one type of stainless steel wherein the matrix is primarily made of the austenite, and the stainless steels are those having the chromium content more than 12%, so that the steel becomes stainless, means it does not get affected by the environmental conditions easily and it maintains its shine. Okay. But when such kind of the steel, when welded, the chromium interacts with the carbon and forms the chromium carbide and creates lot of trouble. So, in this presentation primarily we will be talking about the issues related with the austenitic stainless steel welding, which includes like weld decay, knife line cracking and a stress corrosion cracking. In addition to that, we will also be talking about like what are the mechanisms, what are the factors, and what can be done to avoid the issues related to the cracking in austenitic stainless steel weld joints. And then we will be taking up one case study on failure analysis of the austenitic stainless steel weld joint, followed by the failure analysis, observation and findings. This is one of the most common Schaeffler diagram, okay, that is used to predict the type of stainless steel or the different phases which will be there in stainless steel based on the composition. So, we try to see the stainless steel, as I have said, is one having the chromium content greater than 12% to make it stainless. Okay. So, excessive presence of the means the presence of chromium more than 12% makes the steel stainless. Okay, this is one thing. But apart from the chromium, there are multiple other alloying elements which can be there in steel, like there can be carbon, nitrogen, manganese, okay, silicon, niobium and titanium, and likewise there can be many other elements. So, what we try to do is, based on the composition, we try to find out what will be the different phases in the stainless steel, and that is done based on the two parameters. These are like nickel equivalent. Nickel is basically austenite stabilizer. So, all the factors having the effect similar to that of the nickel, those are taken care of in the nickel equivalent equation. So, nickel equivalent gives you a numerical value accounting the weight percentage of nickel, 30 multiplied by carbon and nitrogen weight percentages, and 0.5 into the manganese content. So, this is what gives us the nickel equivalent. On the other hand, the chromium equivalent is the another parameter, which is basically the ferrite stabilizer. Okay. So, the factors, so the alloying elements which are having, so the chromium is also a strong ferrite stabilizer, but likewise there are many other elements like molybdenum, silicon and niobium, titanium are also ferrite stabilizers. So, their effect is taken care of using the equation of the chromium equivalent. So, by putting the weight percentages of these elements in these equations, equations of chromium and nickel equivalent, the corresponding values of the chromium and nickel equivalent are obtained. Then we try to locate a particular point in this Schaeffler diagram to determine the kind of phases. Say chromium equivalent is 30 and say 15% is the nickel equivalent, then point will be here, which indicates that in this zone there will be two phases, austenite and ferrite. If the point is falling, like say the nickel equivalent is very low, say just 6, then point will be here. If the chromium equivalent is 20 and nickel equivalent is 25, then we will be in completely austenitic state. So, it will be forming austenitic stainless steel only. So, depending upon the location of point identified based on the chromium and nickel equivalent, we will be able to have either just ferrite, ferrite or martensite, only martensite, austenite and martensite, only ferrite, ferrite and austenite and austenite, ferrite, martensite, all three. And with the high chromium content in the presence of carbon and other elements, high chromium stainless steels trend to form the sigma phase, which leads to the increased notch sensitivity and embrittlement of the steels. Okay. So, this is about the identification of the phases in the stainless steel based on the composition. If we talk of the stainless steels having the higher nickel equivalent and the reasonably good chromium equivalent, then the three kind of the problems are commonly encountered. One is the well decay. Okay. This occurs due to the sensitization phenomena, during which chromium interacts with the carbon to form the chromium carbide, leading to the formation of the chromium depleted zones. These chromium depleted zones act as anode and thereby they increase the corrosion tendency selectively. Knife line cracking also occurs due to the sensitization, but at higher temperature due to the different regions. It also leads to the formation of chromium carbide and increased corrosion tendency. On the other hand, the stress corrosion cracking occurs when there are tensile stresses present, suitable corrosive media is there. Okay. So, whenever the material is sensitive to the corrosion and subjected to the tensile stresses, the weld joints tend to crack. Okay. And that decreases the life of the weld joints significantly under the stress corrosion cracking conditions, because both corrosion and stresses work in synergic manner to have the faster crack growth and cause the fracture. Okay. Most of the problems in the austenitic stainless steel weld joints are encountered either in the heat affected zone or next to the fusion boundary. So, this is one zone which is next to the fusion boundary and this is another zone which is away from the fusion boundary. Okay. So, this zone which is away from the fusion boundary experiencing the slow cooling on temperature range of 650 to 850 degrees centigrade. Slow cooling during this temperature in the region which is away from the fusion boundary, this experiences the formation of the chromium carbide significantly if the carbon content is high. What is that? Usually the austenitic stainless steels contain carbon content 0.05, but if it is say 0.07, then this kind of formation tendency is extremely high. Chromium carbide formation tendency is extremely high. On the other hand, chromium carbide can also be formed next to the fusion boundary in very thin zone. Okay. So, this also, but this occurs in the high temperature range of like say 1100 to 1000 degrees centigrade. Okay. So, this kind of the chromium carbide formation will be happening next to the fusion boundary in the high temp, in the zone which is experiencing the high temperature zone next to the fusion boundary. So, this zone is extremely thin, leads to the knife line cracking, and this zone is very wide, which is away from the fusion boundary, experiences the weld decay. Okay. So, these are the two types of the cracking, one next to the fusion boundary, that is knife line cracking, that is observed in austenitic stainless steel weld joints under the, of course, under the improper welding conditions, and the weld decay is another one which is experienced away from the fusion boundary, which is experiencing slow cooling in this temperature band of 650 to 850 degrees centigrade. Okay. Whenever the chromium carbide formation happens, it leads to the intergranular cracking, and that is termed as weld decay. This is what we can explain. So, the precipitation of chromium carbide at the grain boundary is known as sensitization. Okay. So, initially in the matrix, the chromium carbide may be uniformly distributed, but when the things are being cooled slowly in a certain temperature, sensitization temperature range. So, in this band what happens, chromium starts interacting with the carbon and tends to form the chromium carbide at the grain boundary. So, this is what we can see here, this zone away from the fusion boundary experiencing slow cooling in the range of 650 to 850 degrees centigrade. In this case, at high temperature we see at the grain boundaries lot of chromium carbide particles will be formed. So, means chromium which was well distributed in the matrix before the welding, now it will be getting segregated in form of chromium carbide, because these chromium carbides will be having very high percentage of chromium, and this in turn will be leading to the formation of the chromium depleted or chromium deficient zones in the region wherever these particles are being formed. So, this chromium depleted zones eventually start acting as anode. Okay. Okay. And in presence of corrosive media, this will start getting selectively attacked by the corrosive media, leading to the grain boundary corrosion. Okay. Corrosion of the grain boundaries, along the grain boundaries. That is why it is called intergranular corrosion, because at the grain boundary, wherever the chromium carbide particles have segregated and in vicinity of that chromium deficient zones have been formed, they will be attacked selectively by the corrosive media, and this way our the corrosion will be occurring. So, this is basically intergranular corrosion that will be happening along the grain boundaries. This is one, this is called typical weld decay. Knife line cracking, one which is next to the fusion boundary, this is experienced at the very high temperature, zone which is heated to very high temperature for very short time. Okay. So, chromium carbide formation is basically sensitization, and the type of chromium carbide which is typically formed is M23C6, where M represents high percentage of the chromium and little amount of the iron. Okay. And this sensitization means chromium carbide formation happens in a certain temperature range of 600, 650 to 850 degree centigrade. Okay. So, why next to the fusion boundary, why weld decay away from the fusion boundary, not in the other zones? So, this is what we can understand, say this is the weld joint. Okay. This is the weld joint, and we have the 3 weld thermal cycles. Okay. So, let us say one weld thermal cycle is like this, second goes in like this, third goes in like this, right. So, what is happening? The time for which the things are being heated above the 650 to 850 degrees centigrade, this is very short, while the temperature for which the zones which are being heated like 1, 2, 3, zone 2 is being heated in this temperature range and kept at this temperature range for longer time. That is why chromium will have greater tendency to form the chromium carbide in this zone very easily, and this tendency is extremely less. Okay, because this zone is very short. The zone 1 which is next to the fusion boundary is exposed to the sensitization temperature range for very short time, and that is why the weld thermal cycle experienced by the zone next to the fusion boundary plays a crucial role in determining whether the chromium carbide formation will be happening and where it will be happening. Okay. So, the chromium depleted areas wherever the sensitization or chromium carbide formation has taken place, that will start acting as anode, and that therefore, this anodic area will be attacked selectively by the corrosion media, and that therefore, it will be causing the intergranular corrosion. You see, this kind of activity, this kind of phenomena is significantly affected by the strain also, strain or the deformation. If the metal has been subjected to the deformation, then the sensitization tendency is enhanced. Why? Because whenever there are dislocations, then the chromium carbide precipitation, nucleation and the precipitation, that tendency increases. So, dislocation tend to increase the chromium carbide nucleation rate and diffusion rate, and therefore, sensitization tendency is enhanced. So, if we see, this is called a time temperature sensitization curve. What it shows? Here we have time and here we have temperature. Okay. So, this temperature 950 and this side temperature say 550 degrees centigrade. In between, this sensitivity will be extremely high, around say 750 degrees centigrade. And if we try to see, this is like a C shape. Okay. So, here it will take long at higher temperature and it will be also taking long at the lower temperatures, but it will be minimum at a particular temperature. And location of this kind of curve, this is like say time temperature sensitization. So, means this is the time it needs for the precipitation, this is the time it needs for precipitation. This time is very long when the carbon content is low, like say 0.02. So, we will see in the next diagram, like here, if this is the temperature, this is the time, and if the carbon content is low, then it will take a long time to precipitate. If the carbon content is high, it will take shorter time, say 0.02, 0.03, 0.03 and 0.05, or you can say 0.05 and 0.07. So, if the carbon content is high, this kind of the precipitation will be happening very quickly, and we cannot avoid the weld decay in that case. That is why efforts are always made to have the lower carbon content in the austenitic stainless steel, so that the sensitization and weld decay tendency can be minimized. Okay. So, effect of carbon and H net: when the heat input H net is more, then of course, the cooling rate is reduced, and slow cooling in the sensitive temperature range of 650 to 850 degrees centigrade. This will facilitate the easy, because of the long time, it will be facilitating the easy chromium carbide precipitation. So, increasing heat input will increase the chromium carbide precipitation tendency, and also increase the width, which is getting affected because of the sensitization and the weld decay. On the other hand, if the carbon content is more, of course, it increases the sensitization and the weld decay tendency significantly. Why? Because, like say, when the carbon content is low, it takes very long for precipitation, but it does not take much. The carbon content is high, 0.07, 0.05 and 0.02. So, this much time may not be available actually for precipitation during the cooling. So, tendency for the chromium carbide precipitation is minimized heavily when we have the low carbon content, but this precipitation happens very quickly when the carbon content is high. So, this is an important aspect as far as the solution is concerned. So, there are two aspects: reduce the time of exposure in the sensitization temperature range, means use the high cooling rate, this is one, or the second, avoid the carbon content, high carbon content, let us make it like less than 0.02%. Okay. So, that tendency is minimized. Another important aspect is if there are other alloying elements present in the stainless steels or niobium and titanium like chromium, these alloying elements also have greater affinity to the carbon and form their carbides, TiC, NBC and CrC, just like that. But if we see this formation of these carbides and their dissolution as a function of the carbon content, if we see, so here 0.05, 0.1 and 0.2. So, what happens, say 400, 800, 1200, 1400 degree centigrade. Okay. This is the temperature. So, if we see here, the chromium carbide starts dissolving as soon as it gets heated above like say 1000 degree centigrade. Okay. So, this is as a function of carbon content, the temperature above which it will start getting dissolved. TiC then starts getting dissolved, and then NBC starts getting dissolved. Okay. So, NBC is very stable and it remains stable if the carbon content is high, and TiC is further more stable than the CrC. So, if you see the stability means, or the Solves thing, say for 0.05 carbon content, as soon as the CrC is heated above this particular temperature, it starts getting dissolved. TiC, when it starts getting heated above the 1100 degree centigrade, it is dissolved, it is broken into the Ti and C. Likewise, NBC, when heated further higher temperature, then only it gets dissolved. So, which means NBC is the most stable and TiC somewhat lesser stable, and minimum stability with regard to the dissolution is of the CrC. So, if we heat the austenitic stainless steel, simple, then CrC will decompose into Cr and C as soon as it is heated about 1000 to 1100 degrees centigrade. So, this is one way: make the weld joint, give the exposure of 1000 to 1100 degrees centigrade for 1 hour, carbide will decompose into the chromium and carbon and will restore the corrosion resistance. So, even if the sensitization or the precipitation of the chromium carbide has taken place, that issue will be over. Okay. But on the other hand, if there is a TiC and NBC, they need much higher temperature to get dissolved. So, this will be creating another kind of the trouble. That is what we will be seeing in form of the knife line cracking. So, what happens as far as the post weld heat treatment is overcoming the problem of the sensitization and weld decay is concerned? One is heat the weld joint which has experienced the sensitization is above the 1000 heat above 1000 to 1100 degree centigrade, followed by rapid quenching, so that chromium carbide is not formed again. Okay. And if the heat treatment is not possible, then alternative is use low carbon stainless steel, so that the carbon content is in the stainless steel is less, and that avoids the sensitization tendency because of the extremely low carbon, and the chromium carbide formation tendency is minimized. The second way is that stabilize the stainless steel by niobium or titanium. So, when these steels are already available commercially in form of like 321 and 347, these steels will not allow the formation of the chromium carbide, but their own carbides are formed, like niobium and titanium carbides are formed. So, the weld decay problem is avoided, but it leads to the knife line cracking problem. That is another kind of problem. So, why it happens, that is what we will be talking in the next slide. Okay. So, this is the problem which is encountered especially in the stabilized stainless steels. Okay, stabilized stainless steel. Okay, and so these are stabilized using say niobium or titanium. Okay. So, this is another form of the intergranular corrosion. This also happens due to the chromium carbide, but in the different zones. So, mechanism is different. So, knife line attack differs from the weld decay in two ways. It occurs in narrow zone next to the weld metal or fusion boundary. So, it occurs here next to the fusion boundary in the high temperature band of 1000 to 1100 degrees centigrade. Okay. And it occurs mainly in the stabilized stainless steel grade. So, why it is so? Because when the steel is heated, everything gets dissolved, but on cooling, you see, on cooling, since these elements have very strong affinity with the carbon, so even in the short time they are not able to form the chromium carbide. Okay, they are not able to form the chromium carbide. So, what will be happening? Niobium, and wherever the niobium and titanium is there, they will not allow the formation of the chromium carbide, but the carbon will be left as it is. Okay. So, when it is because of this rapid cooling, the nothing is formed, but subsequently when the reheating is done again, these zones will be forming the chromium carbide, and that will be leading to the similar kind of problem, that is the intergranular corrosion. And but since this occurs in very narrow zone, that is why it is called knife line cracking. Okay. But the weld decay occurs over a wider area and far away from the fusion boundary. Then stress corrosion cracking, this occurs especially when the three factors are present, like material which is sensitive to the corrosion, there are enough so material is one, then corrosive media and enough tensile stresses. So, when all these three zones are present, then only stress corrosion cracking will be happening. Okay. This is stress. So, there is a need of tensile stresses, sensitive corrosive media, and the metal which is sensitive for this kind of the attack. So, sensitive material, corrosive media and tensile stress. Whenever it happens, the intergranular corrosion through the granular galvanic cell formation will be taking place, and corrosive media and the stresses work together in a synergic manner to cause the fracture very rapidly. So, in this case what we use K1SSC, okay, SCC. So, this is called stress intensity factor in the stress corrosion cracking environment. Actually, that is what is determined, and this comes out to be extremely lower than the K1C only. Okay. So, this value may be like 10 to 20 times lower than the K1C. So, if we see K1SCC will be roughly like say 1 by 10 to 20 times of K1C. So, if the K1C is being compromised very badly, then no design will be able to survive if the K1SCC has not been kept in mind. So, now we will take up one case study that is on the failure analysis of the component made of the Austenitic stainless steel weld joints. So, a structural member of a component used in food processing industry made of the AISI 304 austenitic stainless steel, and the weld joint of the component failed prematurely within 1 year of the service, which was being used in the NaCl environment, NaCl rich environment. and therefore investigation was carried out to see, and it was found that the material is made of as specified. Composition of the material is same as a specification, design as per recommendation, and welding was done using matching filler using GMAW process. Everything is good so far. Visual examination showed the cracking away from the fusion boundary in the HZ of the weld joint. Mechanical properties were as specified, fine grain austenite in the weld but coarse grain structure in the heat affected zone. Okay. And NDT shows no defect whatsoever, normal operation, maintenance not applicable, and XRD shows that the chromium carbide formation and selective depletion of the chromium from the grain boundary region in the heat affected zone. So, this is a typical indicative of the sensitization. Okay. Sensitization means chromium carbide formation is taking place, that will be leading to depletion of the things. And when the stereoscopy and SAM was carried out, corrosion was observed in the heat affected zone, and it was intergranular type of corrosion, and comparison indicated like chromium carbide formation in the heat affected zone of the failed weld joint, and which was absent in the new one actually when it is exposed. So, the corrosion attacked selectively in the heat affected zone. So, all above suggested that like failure by intergranular corrosion caused by the sensitization and weld decay due to absence of proper weld heat treatment. Okay. So, now I will summarize this presentation. In this presentation basically I have talked about the austenitic stainless steels, different types of austenitic stainless steels, and more particularly the common issues encountered in the weld joints of the austenitic stainless steel. We have talked about the mechanisms contributing towards the weld decay, knife line cracking, and stress corrosion cracking, and what can be done to avoid the issues related with the cracking in the austenitic stainless steel weld joint. And finally, we have taken up one case study on the failure analysis of the austenitic stainless steel weld joint. Thank you for your attention.